So now we're ready to start investigating the cardinalities of infinite sets and trying to compare multiple types of infinity. So in this video, let's explore whether or not the cardinality of the natural numbers is equal to the cardinality of the integers. And recall the natural numbers are 1, 2, 3, going on forever. The integers are the natural numbers plus 0 and all the negative whole numbers. So now if we want to show that these have the same cardinality, we would want to show that there's a bijective function between the two. And if we want to show that they have different cardinalities, then we have to show that it's impossible to create a bijective function between the two sets. So now you can think for yourself a little bit, which do you think is correct and how can you prove it? So try to take some time and think about that. You can pause the video. Now I will go ahead with working on the solution. So your first intuition might say that the cardinality of the integers must be larger. All of the natural numbers are in the integers, but there's also a whole bunch of other elements, 0, -1, and infinite more elements. However, this is not quite enough to say that the natural numbers has a smaller cardinality than the set of integers. Essentially what you're trying here is you're trying to produce a one-to-one pairing between these two sets. So let's write out a few of the integers here. So if you are trying that most intuitive pairing where a natural number maps to itself, so this is the set of integers here, and then you could try, I'll just write the natural number underneath that's supposed to map. So you could try writing the natural numbers like this and having them mapped from here to here, 1 to 1, 2 to 2, 3 to 3. This function would be f of x equals x. But clearly this fails. However, showing that there's a function which fails to be bijective between the two sets does not mean that there is no function that is bijective between the two sets. So this is not good enough to prove that the integers have a larger cardinality than the naturals. So now we can try and come up with another bijective function between these two sets. And only go ahead now if you're ready to hear the actual solution. So there is in fact a bijective mapping between these two sets. And in fact, the set of natural numbers does have the same cardinality as the set of integers, as unintuitive as that may seem. So here's a way that you can create a bijective function between these two sets. You can have 1 mapped to 0. And so the last time the issue was that we never got to any of the negative numbers. We never had any natural numbers mapping to 0 or any of the negatives. So we can start here, we can go to 2, but if we keep going this way, we're going to still miss all the negatives. So instead, how about next we go over here and say the 3 maps to -1. And now we can keep alternating between these two sides. And this way, you ensure that eventually you get to every integer. And now you can give me any integer you want, and I can tell you which natural number is mapping to it using this function. So this is an intuitive way to think about this mapping, and it's quite clear that it is injective, meaning that all of the natural numbers map to different integers because we're moving every time. We're flip-flopping and never having two natural numbers mapping to the same integer. And we can also see that it's onto, and this part is where you can give me any integer you want and I can tell you what the corresponding natural number is. So if you were to give me 5, for example, I would just have to keep going. 8 would map to 4, 9 would map to -4, 10 would map to 5. And so we can also write this function explicitly instead of just this intuitive way. And let's try to do that right now. So we're going to write a piecewise function because this kind of flip-flopping doesn't translate into any simpler kind of function. So we can say that, first of all, you can see that the even numbers all map just to themselves divided by 2. So we can say that f of x equals x divided by 2 if x is even, then what is the function here when x is odd? So in the case of 3, you get to -1, 5 you get to -2, 7 you get to -3. So just think about this for a second, see if you can come up with it yourself. And in this case, the way to do this is to say f of x equals x minus 1 divided by -2. And this is if x is odd. And so let's just see that this works. So 1 minus 1 is 0, divided by -2 is still 0, so 1 maps to 0, that's correct. 3 minus 1 equals 2, divided by -2 equals -1, so that worked as well. 5 minus 1 equals 4, divided by -2 equals -2, and that works. And you can see that this is going to continue to work for all of the odd numbers and continue to represent all of the mappings over here. So this function right here is a bijective function from the natural numbers to the set of all integers, and for that reason we can say definitively that in fact the cardinality of the naturals is equal to the cardinality of the integers. And that's an unintuitive solution, but it is in fact true using this argument. Thanks for watching.